let's talk about 8.2, the law of cosines. So the law of cosines says that by deriving rules from right triangle properties, the law of cosines gives that a triangle with angle alpha opposite side A, angle beta opposite side B, and angle gamma opposite side C, that, and then there's three different parts, just like the law of sines. You may notice this first part, especially for this guy down here, it looks very, very similar. All three of these look almost exactly like the Pythagorean theorem. And indeed, if alpha is your 90-degree angle in this version, it's 90 degrees here or 90 degrees here. Since the cosine of 90 degrees is 0, this entire term would die, and this would be the Pythagorean theorem. However, this is a more general Pythagorean theorem. So it says that a squared equals b squared plus c squared minus 2bc cosine alpha, or b squared equals a squared plus c squared minus 2ac cosine beta, or c squared equals a squared plus b squared minus 2ab cosine gamma. Remember, here's how you read it in general. A side squared equals the sum of the other two sides squared minus twice the product of those other two sides times the cosine of this side's corresponding angle. So notice that we have angle alpha and A go together, that angle beta and B go together, and angle gamma and C go together. Otherwise, there's a C over here, so there are no C's over here, and it's just the other things. It's the sums of the squares of the remaining two things minus twice the other two things times the cosine of the corresponding angle. It will always look like that. All right? So get that down, and then we're just going to do a few examples. So it says in an angle with sides A, B, and C, with angles alpha, beta, and gamma, it says that A is 10, beta is 30 degrees, and C is 12. It wants you to solve ABC using the law of cosines. So the triangle ABC using the law of cosines. And you can assume that alpha is opposite A, beta is opposite B, and gamma is opposite C as usual. So we're just going to draw this. Now, I do not know for a second if this is to scale, but I'm just going to draw it the best I can. So I'm going to try to draw beta as a 30-degree angle. Something like that, I don't know. And it's not necessarily a right angle, so let me not draw it as a right triangle. So here's your triangle. And you know that you have right here beta equals 30 degrees. That's this guy. And then you've got your other two guys up here, alpha and gamma. Okay? So you've got alpha and gamma. And then you have that A is 10 and C is 12. Like this. So we want to solve ABC using the law of cosine. So this is a side angle side. The law of sines isn't going to work here. And we know that the law of sines isn't going to work here because we don't have any two things that correspond. We only have one of this pair. Okay? We only have one of this pair. Or rather, we only have one of this pair. And we only have one of, if this is little b, we only have one of that pair. You need two of a pair to do anything with the law of cosines because you have to relate the ratios. So what we have then is we're trying to find b, and we're just going to use the law of cosines for it because we do have enough information. So from the law of cosines, it's b squared equals a squared plus b plus c squared, okay, minus 2ac cosine of whatever went with b, so beta. Now I'm just going to plug everything in. So then we have that b squared, which we don't know, is a squared, so 10 squared, plus c squared, which is 12 squared, minus 2 times a, which is 10, times c, which is 12, times the cosine of beta, which is 30 degrees. So then I have that b squared must be 100 plus 144 minus 2 times 120 times the cosine of 30 degrees. Now, we actually do know the cosine of 30 degrees. If you go and look at your unit circle, the cosine of 30 degrees is going to be the longer of the two. The x is going to be the longer of the two, so that tells me it's going to be root 3 over 2. Okay. And we're going to look at this, and we're going to see, well, there's a 2 here, and there's a 2 here, so those two cancel. So this is 120 root 3. So b squared is equal to 100 plus 144, so 244 minus 120 root 3. And then we're going to take the square root of that. So we should probably approximate what this is and get some sort of answer. Technically, if you take the square root of both sides and take the positive square root, as in you literally write this, that is an answer. That does technically work. But we're probably just going to want to approximate this. So let's figure out what b squared is approximately. And then let's just take the square root of that and get an answer. So if you go take a 244 minus 120 square root of 3, and you plug it into a calculator, you'll get somewhere around 36.15, it looks like. So about 36.15. So then we get that b squared is about 36.15. But you'll notice that we're solving for b and not b squared. So we have to take the square root of both sides. So then b is about the square root of 36.15, which is itself about, I don't know, like 6.01 or something. So if we just put in 6.01, there we go, 6.01. So we know that b is about 6.01. That was the math on it. We just plug it into the law of cosines and we're done. So 6.01. All right, so let's keep that in mind, 6.01, and I'm going to go ahead and label that, and I'm going to reclaim this space to do something else. So is about 6.01, or honestly, if you're this close to it, 6 is probably fine. But if I asked you for 2 decimal places, 6.01. So just look at whatever the problem asks you for. And now we just need to find the other 2 angles. Now, you could use the law of cosines at this point to find alpha or beta if you wanted to. You could take either version of it and plug it in. You could even do the exact same thing with b again if you wanted to. But I would take a or c and plug this in and solve. But at this point, you can also just solve for alpha or gamma using the law of sines. That's easier, so let's do that. Let's just use the law of sines to solve for the rest of it. We needed the law of cosines to get this, but we can just use the law of cosines to find everything else. So let's say that the sine of alpha, and we want to solve for alpha, so the sine of alpha is to 10 as, let's say the sine of beta, which we know to be 30 degrees, is to that 6.01 we just found. And now we can just solve for alpha the normal way. That is, you multiply by 10 and take the inverse sine. So alpha is going to be the inverse sine of 10 sine 30 degrees over 6.01. So you just go shove that bad boy into a calculator, and you get about 0.982 radians, or 56.3 degrees. So 56.3 degrees is what we'll go with. So alpha is about 56.3 degrees. And since we know that alpha is 56.3 degrees, at this point, since we know 2 of the angles, we could find the remaining angle, gamma. So gamma is just going to be 180 minus 30. So 180 degrees minus 30 degrees minus 56.3 degrees. So that's 150 minus 56.3 degrees. So that's 93.7. Yeah, 93.7. So that's 93.7 degrees. And we've solved for this. 93.7 degrees. So we found that. We found that. We're done. We've solved every single part of it. So we only needed the law of cosines to find one other piece. And then we were able to use the law of sines to find the angles and this little trick that we've known since geometry. Now, if you wanted to, and I'm just going to set it up, we could rewind way back in time, and back in time to this point in the problem, and we could say, okay, we want to find alpha now. So we could say then that 10 squared, which is a squared, equals b squared plus c squared minus 2 times a, or 2 times b times c times the cosine of alpha. And you could solve this whole thing for the cosine of alpha. That is, you could subtract over the 6.01 squared, subtract over the 12 squared, and then divide by negative 2 times 6.01 times 12, and then take the inverse cosine, and that would also give you an answer. So you could come out of all of this. I would simplify down all these numbers first, and you would get a single number here and a single number here. So you would subtract this number over, you would then divide by this number, and then to get rid of this cosine, you would take the arc cosine of both sides. That would also give you the exact same answer for alpha. So if you want to use just the law of cosines, you're more than welcome to. I just think that that's a lot more work. Completely up to you. So let's do one more example of these, and it says that in a triangle with sides the same way that it was last time, it gives you A, beta, and C. Side angle side triangles are kind of what the law of cosines is made for. So let's do another side angle side. And this time it told me that beta was once again 30 degrees. So that's cool. So you may notice that this is like really close to exactly the same problem. And guys, when I say really close, I mean it's exactly the same problem. So just to show you that this thing will work on anything, let's just solve this if this were 130. Why not? Let's just make that 130 degrees. So let's make it a nice big old oblique triangle, 130 degree angle, something like, I don't know, this, I guess. 130 degrees. It'll work on a triangle even like this. So you know that this thing has side, let me do it better than that. So you know that one of these sides is 10. This thing's 130 degrees. This is 12. And I want to solve for every other part of the triangle. So I know that A is 10. We know that C is 12. Okay, which makes this down here the side opposite C, which is gamma. And then that makes this alpha. And of course that's beta, which makes this B. So now we can solve for everything. So I want to know B. So B squared equals, okay, take one of the other sides and square it. And add to it the other side squared. And then subtract 2 times the same two numbers you just wrote, 12 and 10. And then it's the law of cosine, so it's cosine of whatever angle goes with B, so beta. Beta in this case was 130 degrees. Okay. Now I don't know what these numbers are off the top of my head. Cosine of 130 degrees, I have absolutely no idea. But B squared equals, again, 144 plus 100, okay, minus 240 times cosine of 130 degrees. Just type this into a calculator, you'll get something. So we get that the B squared equals round about 398 or so. 398.27 it's telling me. So 398.27. Okay, now please don't write 398.27 here. Please don't do this. Okay, don't do this. Remember, you found B squared. You're looking for B, so we have to take the square root of both sides. So if we take the square root of that, so 398.27. If we take the square root of that, then B is equal to, or is approximately equal to, the square root of 398.27, which is, to about 2 decimal places, something like 19.96. So about 19.96. So B is about 19.96. Now I want to find either alpha or gamma, and then the other part is easy as pi to find. So let's work with, I would do the law of sines here if I were you. I would do the law of sines. But just to show you how to use the law of cosines, you verify that it's the same. Just to show you how to use the law of cosines, I'm going to use the law of cosines again. So remember, B is about 19.96. I'm just going to rewind all this. So 19.96 for B. So that's about 19.96. Okay. Now, I personally would set up, if I wanted to find alpha, I would say the sine of alpha over 10 equals the sine of 130 degrees over 19.96, and then solve for alpha really quickly. But if you want, we can say that 10 squared, this is using the law of cosines to do it, just so that you have an example. I wouldn't do it this way, but you can do it this way. So I'm using the version with a. So a squared equals b squared plus c squared minus 2 times b times c times the cosine of the thing that we're trying to find. The reason I chose a over here is because we're looking for alpha. Okay, so that's 100, okay, equals 19.96 squared is round about 398.4016. But we're just going to go ahead and add this 144 to it to get 542.4016. So 4, that's fine. 4016 rounds to that. Minus, so I've already done both of these. That's what that is. Okay. Minus 24 times 19.96. I did 2 times 12 to get 24 times 19.96 is about 479.04. So 479.04. So that's it. 479 cosine theta. You want to leave the exact decimals in here as big as you want to the entire time. You will get more accurate answers. But in order to solve this, you're going to do you're going to subtract over the 542.4 and then divide by negative 479. So you're going to get that the cosine of alpha equals the 100 you had minus the 542.4 that you subtracted over, and then you divided by negative 479. And so if you do all the math on that, you better get a number that's a fraction between negative 1 and 1. We can get negative 1 or 1 here, but it better be a number like that. And we do. We get 0.92359 something. 0. And the more of this that you put in, the better. 0.9236, let's say. And then in order to find alpha, of course, you've got that the cosine equals that. So you have to take the arc cosine or the inverse cosine. So it's the inverse cosine of, and honestly, I would just wrap this in parentheses and put the inverse cosine in front of it and be done with it. That's how I'd do it. Or I'd say the inverse cosine of answer after you have this loaded up already and you've pressed enter and you've got it like sitting there. It's whatever you want to do with it, but 0.9236, and you get, and then you'll probably get it in radians unless you have it in degrees. I would recommend putting it in degrees unless you want the extra step. But when you do this math, it'll throw out something around 22.54 degrees. So 22.54 degrees. So that's what alpha was. So alpha was about 22.54 degrees. You could do the exact same thing for gamma. You could do c squared equals a squared plus b squared minus 2ab cosine gamma and solve for it the exact same way. But now that you have two angles, I would just do 180 minus 130 minus 22.54 and be done with it, which is what we're going to do. You could also use the law of sines to find gamma, just cause. I would only ever use the law of cosines to find the missing side in a side-angle side triangle. Otherwise, I would use law of sines for everything else. As soon as you have enough information for law of sines, revert back to it. It's way easier to work with, as you can see. But gamma, and by the way, you may notice that gamma is written like that when it's typeset by a computer, and it's written like this when it's written by any human. That's just how it's done. But gamma is equal to the 180 that the triangle has to add up to, minus the 130 that we already had, minus the 22.54 that we already had. And when you go through and you do all of that math, you get a number in the neighborhood of, I don't know, 27.46 or something. 27.46 degrees, of course. So we plug that in so that we've actually solved our triangle. And it's approximate. It's approximate because we used an approximate figure in the math itself. And we're done. We've solved it. So that is the last of the law of cosines. There's one more thing that I do want to talk about, but I hope that you don't have any big problems with this. Now, remember the way that I would have set this up, if we rewind, the way that I would have set this up instead of doing all of this math, I would have instead just set up, let me actually just rewind back to that part of the problem. Let's just go all the way back in time real quick, and let's solve for gamma again, except I'm not actually going to solve it, I'm just going to set it up. I would have said, okay, I want to find gamma, okay, but we're going to have to use this law of sine. So the sine of gamma, okay, is to the side opposite, 12, as the sine of something that we know, we know 130 degrees. The sine of something that we know is to 19.96. Okay, I would have multiplied both sides of this by 12, taken the inverse sine rather, and you would have been done. You'll get the exact same answer, and then do the 180 minus thing, and you're done. That's literally it. That's literally all that there is to solving these things every single time. So I would do this way, but notice that this doesn't work unless we know this number. We had to use the law of cosines. We had to use the law of cosines to find that number, this b here. So that's where the law of cosines comes in this specific case. All right. Anyway, I'll let you finish that up, verify that my math is close. Now, you may get a number that's a couple decimals off, but if you get something radically different, ooh, that's interesting. You might want to take a look at your math and see if maybe you did something wrong. But you should get a number that's very close, maybe within 1/10 of a decimal. Since remember, we did round the other time a lot. So you may not get exactly the same number, but you'll get really, really close to it. So let's talk about this definition here real quick in a really easy little example, and then we're done. So if the sides of an oblique triangle are A, B, and C, then the area is given by A, the area, is S times S minus A times S minus B times S minus C, all under a square root. Where S is the distance halfway around the perimeter. A plus B plus C, that's the perimeter, divided by 2, that's halfway around. And we call that S the semi-perimeter of the triangle. So we need to find the area of a triangle with side lengths 7, 10, and 15. Easy enough. So we've got ourselves a triangle with side lengths 7, 10, and 15. We don't need to draw triangles for this. We just plug it into a formula. The things that we need is S. So let's find S. So to use Heron's formula, we've got to find S. So S is 7 plus 10 plus 15 divided by 2. So 10 plus 15 is 25, plus 7 is 32, divided by 2 is 16. So then the area is the square root of S, which was 16, okay, times S minus A, so 16 minus 7, times S minus B, so 16 minus 10, times S minus C, so 16 minus 15. Therefore, we get that this is the square root of 16 times 9 times 6 times 1, okay? And you just do this math real quick. And you do 16 times 9 times 6. You don't have to worry about the times 1. You get 864. So 864. And then the square root of 864 to about 2 decimal places is about 29.39. So 29.39. And I didn't give you units on this, so it's just square units if you want square units. And there you go. You got the area. And all you had to know was the distance around. And that is, well, that's useful for a triangle. You don't have to know anything about its angles. Nothing about its angles. I can still tell you its area just by knowing the sides. So awesome. That's Heron's formula. If you ever see it out in the wild, now you know how to apply it. And that's all.